Oh. Okay. So let's continue with linear regression. So just as a quick reminder, last time, just as a summary, what we're doing when we are trying to do a linear regression or fit a line through my data that is in some sense closest to the data, what we do in that process is we take the measured value of my data, this is y I measured, and I take the model, which in this case is the linear model. So in this case, linear regression case, this is going to be A0 times A0 plus A1 times X. Okay. And I look at that difference, this error between the two, and take a square of it. And we are trying to minimize this sum. And the way we minimize things, we know that what has to be true is that the partial derivative with respect to both of these parameters has to be 0. And that's the procedure we completed in that worksheet that we worked through last time. Now, when we solve for that, we literally get that A0 should be this and that, okay, for my linear model. Okay. So now your assignment would be literally to implement that. Okay? So given data x and y, so I will have n points. Okay? I will come up with A0 and A1 and actually then plot the result to see that we can actually really do the fit. Okay? So I have already posted a linear regression template. It's a Python notebook and it's been posted on Canvas. So start from that, download it please. Okay. This is the template. And I have already typed in the data, so you don't have to go to the data. So these are going to be NP arrays, so of course I have to import NumPy, and then my X is this data, 2.5, 3.5, 5, 6, and so forth. My Y's are 7, 5.5, and so forth. And then we're just going to quickly plot them. So if you execute that tab, you should get something like this. So data is a little messy. It's not a single function, nice, smooth function, any in particular. Now, one thing that I will immediately note about this data is that however I try to do the straight line, it's not going to be a super good fit to this, because straight line, it's either going this way through here, or I kind of see two slopes really to this data. So straight line is not the best fit, but nevertheless we're going to attempt to get it. So what I want you to fill in here right now, I just have A0 is 0 and A1 is 0, but you want to replace this with proper code that computes A0 and A1 based on the data x and y. And data x and y has been given here and is input to this function. And then you're going to execute this function and plot the comparison. So right now, this comparison is bad because I'm plotting zeros, okay? But this is my model. My model is going to be A0 plus A1x, okay? So let's get going. Niku and I will walk around and help as necessary, but let's work on it for about 10 minutes and then see where we're at. And actually, unless you, so give me a call and I'm gonna disconnect the video since you do have the slides, you do have the thing. So I can solve it in parallel as well. Oops. This is what you're aiming for. So how are the for loops coming along? So maybe this slide is more useful. So you need all of these sums. You need to compute the sums based on beta x, y, and y. So once you have all of the sums, then you just put them together in this formula. If you can find some function, you can use that. I did it with for loops. It's good exercise for for loops. So each of these sums that has the sigma sign has to be computed separately, independently. Then it's one for loop that computes all of them at the same time. Okay? But you have four separate sums that you need to compute in the same for loop. Yes, in the very beginning, you have to initialize all of the four sums. You give them a name, and each of them is initialized with 0. And then I have one for loop, and that for loop keeps adding to each of those four separate ones. So I'm calling my sums sum x, sum y, sum xy, sum x2, which is sum x squares. So each of them is initialized at 0. And then in a for loop, I add x's to sum x, y's to sum y, xy times y to sum xy, and sum square. Yeah? Now it looks simple, right? Yeah, you can't do all at once. No, because there's all separate sums, so mathematically it's not the same. I've noticed the number you do that, don't add it all at once. They have to be separately computed. Because think about it, let's say that there is 7 numbers here, okay? It's sum of 7 numbers times sum of another 7 numbers, okay? It's not the same as sum of this first one times the second one. So now that you have this right, you put it together in the... So this sum x, okay, will be this sum here in the formula. Sum xy will be this one. Sum x squared will be this one. And sum y will be this one. Okay? So those are these 4 sums. And those are all the 4 that I need. And then my A1 is I just follow the formula. And A0, it's on the code, well, on the slide I had A1 was listed first, so I just went with it. But these are just then straightforward typing in. Yes. Oh, okay. This is a shorthand notation. So this is what I wrote here is the same as this. At the beginning of the code, I avoided using this shorthand. I'm going to leave 2 like this, and I'm going to say same as sum xy so you have code, because I'm going to upload this code. And this is power of 2, right? So again, key in implementing this formula based on the data is, well, figuring out how far does this sum need to go. So I need to figure out number of elements, which I put in code for you already. So n is length of one of these arrays. And then I do a for loop. I initialize all sums as 0. I add all elements. Here is a typo. There's always a chance for typo. And then I just type in this formula, basically carefully following this. And when I execute that, I plot the data. Again, my model, which I called Y model, is this A0 that I computed plus A1 times X. So it's my line model. So I plot that model against the data, and you should get something like this. So that's in your last cell, so you just need to execute it to get it. Are there any conceptual questions here other than typing things correctly? That's always a problem. Somebody got it. Okay. One person in the class is definitely detected. Because after this, I want to move on to something better, because quite frankly, I'm not happy with this. This is a poor representation of data. Okay? It's kind of like it should curve a little better. And for curving, I have to have another model. Straight line model will not do. Do we agree on that? Okay. So let's look at how do we do that. And we're going to go through something called linearization of nonlinear relationships. So often I have to look at the data, and I looked at the data. A straight line, yeah, I can fit it, but it's not a good fit. In this case, this is a good fit, but there, in the first plot, I need something that is curvy. So let's assume in the most simple case that I want to fit a power law. And the joke is that if you can't fit the power law or find the powers that fit this type of relationship, you didn't try hard enough. So power law is very common when I have data vary over multiple orders of magnitude. And there are two versions. There is an exponential version of it, and then power law is the second one. So let's focus on, let me see which one will I want for this one. Power law. Let's focus on this second one. So let's say that I'm trying, instead of my linear relationship, A0 plus A1x, let's try fitting this type of, let's try to fit our data as y is equal to A2x to the B2. Now, I could follow the same procedure as we did on the worksheet and try to get that. However, the set of equations I would get to solve would be a set of nonlinear equations. Those we haven't covered, for one. There is a version of Newton-Raphson for systems as well, but we haven't covered. And are also simply harder to solve. But I can actually go and try to be smarty pants about it. Let's take a log of both sides. In that case, my log y is equal to log of A2 plus B2 times log of x. Do we agree? Once I take the logarithm of both those sides, I will have logarithm of y, that checks off. And then I'm going to have log of A2 times x to the B2. Okay? When I have multiplication, I know that I can break that up as log of A2 plus log of x to the B2. And that exponent B2 just kind of falls down when I do logarithm. So I will get this. Everybody agrees with my basic calculus here? Okay. So when I look at this relationship, it is a linear relationship between log of y and log of x. Yes? If I define new variables, log of x and log of y, the relationship between them is linear. Is that correct? So I can use my linear regression that I just did to try to make that fit work. So I'm gonna now, instead of fitting x and y, I'm gonna fit log of x and log of y. Let's do that. And I'm gonna write myself notes. I'm gonna insert here a new one. So I'm gonna do power law fit. Linearization claims that log of y is log of a2 plus b2 times log of x. And my log fit is, and I'm just using a2 and b2 in order not to confuse with that a0 and a1. x2, b2. And let's use, I'm going to use Python. Okay. So I'm assuming this power law fit, and if I do log of both sides, I'm going to get this. Great, so then I can actually use my linear regression and I'm going to call these two uppercase A0 and A1 to get for NP log of x and NP log of y. So I'm going to take logarithm of both x and y, and I'm going to give it to my linear regression. And that returns two coefficients. Everybody following so far? Now, how do I actually get my A2 and B2 once I have this A0, A1? So what my A0, A1 assumes, it assumes that my log of y is A0 plus A1 times log of x. Because I gave it log of x and log of y as data, right? So what is my A2? How do I get A2? How do I get B2? What is A2? What is B2? Give me half a minute here to tease that out of you. So my B2 is A1 and log of A2 is A0. Yes? So I can compute what my A2 and B2 is and use that as this power law fit. And we're going to show that result next time. Actually, that's a great little quiz to complete by next time. So I'm going to say compute A2, B2, and plot the comparison between power law model and data. Yes? I'm going to repost this template so you can complete. Next class, just before the class. Whenever before the class.